So here we go. Weight is the force of gravity on an object. So how much would your weight change if you moved from sea level to Mount Everest to the International Space Station? And then a few pieces of information. Earth's mass is 6 times 10 to the 24 kilograms. Let's assume that your mass is 75 kilograms. And then Earth's average radius is 6,371 kilometers. The elevation at the top of Everest is 8.8 kilometers. And the ISS, meaning the International Space Station, orbits at an altitude of 350 kilometers above Earth's surface. Okay, so let's write out some of those facts to kind of help us make sense of this a little bit. So first of all, we're told that Earth's average radius is 6,371 kilometers. So I'm going to call that the radius of Earth. It's 6.371 times 10 to the 6th meters. So I'm converting that to meters. And then the height above the Earth of Everest, and I should say above the surface of the Earth, is 8.849 times 10 to the 3 meters. Okay, so specifically I'm taking kilometers here, here, and then here, and I'm converting them to meters by multiplying by 1,000. And then if I'm using scientific notation, I'm putting a single number in front of the decimal point, right? Finally, let's write out the height above the Earth's surface of the International Space Station. So that would be 3.5 times 10 to the 5th meters. Now that I have this key information in meters, and I'll have my masses in kilograms, now my units will work out so that when I'm using that gravitational constant of 6.67 times 10 to the minus 11, units will cancel and I'll end up getting newtons for my force. And then let's draw some of these out. So here's the radius of Earth, right? We're going from here to here. That's our Earth. And then the height of Everest, so we've got to imagine that we have, a mountain over here. Here's snow on top. And we're looking at just the height. So that would be from here to here. This straight line height, that's the height of Everest. And then the orbital altitude of the International Space Station would be from right here to here. So this distance right here is that height above the surface of the ISS. Okay, so we've got 3 pieces of information. I'm going to clean up this Everest one a little bit, so this is a little bit more obvious. So we're talking about from here to here. Okay, now when we're looking at these 3 distances, remember the distance that matters is the distance between the centers of the masses. Okay, so we're going to be thinking about a person who is having a hard time picking the right color here. A person who's, standing on the Earth's surface, and then that person is standing on Everest, so then moving over here, right? And then that person is now located on the ISS, so then they're going to move over to here. So their distance from the center of the Earth is going to change each time. How will that affect the force of gravity on them at those 3 locations? So let's start at the surface of the Earth, which is at sea level. So at sea level, the force of gravity is equal to G times M1 times M2 divided by the distance between them. So M1 is going to be the mass of the Earth, and M2 is going to be the mass of me. And then the distance between me and the Earth, if I'm standing at sea level, is just the radius of Earth. That's the distance between those centers of mass. Plugging in the numbers, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of Earth is up here, 6 times 10 to the 24 kilograms, times the mass of me, that's 75 kilograms, and then divided by the distance between us, radius of Earth, 6.371 times 10 to the 6th meters. I got that from right here. Okay, so if you're plugging this into your, and do not forget this, square, right? Square that denominator. It's an inverse square relationship. So if you're plugging this into your calculator, you've got to be careful to maintain the scientific notation. And then when you're dividing, you want to put the denominator in these parentheses before you square it. If you do the calculator work correctly, you will get 739.5 newtons. Okay, so that's our kind of baseline weight at sea level. But what happens to weight if we go to Everest? And think about it, is if the weight does change, is it going to get weaker or stronger? So at the top of Everest, you're now moving farther away from the center of Earth, right? So here we go. Let's rise up on Everest. Same equation. Same masses. But the distance between the centers of those mass is different. So now what we need, so we're going to go from the center of Earth to the top of Mount Everest. That means that we need to use, for the distance, the radius of Earth as before, but plus the height of Everest. And we're going to square that. So we're going to get our 6.67 times 10 to the minus 11. I'm going to skip the units because I'm running out of space, and you can see the units in the example above. The mass of Earth is still 6 times 10 to the 24 kilograms. The mass of me is still 75 kilograms. And now I'm going to divide by the radius of Earth, which is this 6.371 times 10 to the 6th meters, plus the height of Everest. So it's right here, 8.849 times 10 to the 3rd. That's meters. Don't forget to square it, okay? And if you do the calculator work correctly, you will get 737.4 newtons. Now, why are the units coming out as newtons? Well, let's take a look at the example above where I actually carried out the units more obviously. So if you look in the numerator, you've got kilograms times kilograms, but then you have kilograms squared down here. So those cancel. And then if you look at the denominator, you have meters squared. And then you have meters squared here. So those cancel. And what is left uncanceled is newtons. Okay, so that's why the answer comes out in newtons. I can show that one more time here. This is Newton meters squared per kilogram squared. Okay, so this kilogram times this kilogram divided by kilogram squared, those go away. And then I've got meters squared on the bottom. That cancels with meters squared on the top. And so what's left is newtons, and that's why I have newtons here. So from 739 to 737, did you get heavier or lighter? You got a little bit lighter, right? 2 newtons lighter. Let's go to one more location. Let's go to the International Space Station. Now we're going to move quite a bit higher. Okay, Everest is only about 30,000 feet above sea level, which is 8.8 kilometers. But now we're going to go up to the International Space Station, which is in low orbit above the Earth, but it's orbiting at an altitude of 350 kilometers. So the force of gravity up there at the space station, you're still going to have the same constant G. You're going to have the mass of Earth. You're going to have the mass of me. And now the distance between the person and the Earth is the radius of Earth plus the height above Earth of the International Space Station. Don't forget to square it. This is the 6.67 times 10 to the minus 11. The mass of Earth is still 6 times 10 to the 24 kilograms. Mass of the person is still 75 kilograms. Radius of the Earth is 6.371 times 10 to the 6th meters. Plus the height of the International Space Station is 3.50 times 10 to the 5th meters. Okay? Squaring that in the denominator. If you do the calculator work correctly, you will get 664.5 newtons. So check it out. We're even lighter than at the top of Everest. Okay? And in fact, if we could zoom all the way out, we would notice that we are significantly lighter than at sea level. Okay, from sea level all the way to the International Space Station, we have lost 75 newtons. So this is 75 newtons less than at sea level. And you might be wondering, okay, 75 newtons, I don't totally have a grasp on how much weight that really is. That is approximately 17 pounds. So that's pretty significant. All right, so to recap, the force of gravity between two objects is related to their masses and the distance between them. Okay, and we can see in this example that as you increase the distance between the masses, you do see a decrease in the force of gravity between them.